General relativity, step by step. I'm going to go back to my line element squared, line interval squared, plus a of t times the r squared for the radial terms plus q of r squared times the angular terms. And what did we have? We had d theta squared plus sine squared theta d phi squared. There we go, and I'll close those brackets. And we've got this nice expression for our trial element here. You'll remember that a of t was our Hubble term, a spatial expansion term, and q of r was, we had three different solutions for that. We had that it was equal to r0 sine of r over r0, or just plain old r, or r0 shine r over r0. So we've got that, and I've spent some considerable time talking about this. I'll return to it later, but for the moment I'll just treat that as finished. What I'm going to do in this and the next 2 or 3 screencasts is talk about the Hubble term. I want to see its long-term evolution. I want to see if it's going to go to a maximum and then get smaller again. I want to see how this function a of t behaves as a function of time. Okay, so how do I do that? Well, we need to go back to CSS 015, and we had the Einstein field equations for our trial metric here for no, it wasn't for a dust, it was for a perfect fluid, which had pressure and density. And the equations that we had were these. We had 3a dot dot. Remember that a is just a function of time, and a dot dot is just d2 by dt squared of a of t. So it's just differentiating twice. Equals cosmological constant minus 4 pi g, and then I had rho 0 plus 3p0, and the other equation that we had was a little bit more involved. It was I'll need more space, a dot dot over a plus 2a dot over a squared minus 2q dash dash over a squared q, and that was equal to cosmological constant minus 4 pi g times rho 0 plus p0. A formidable looking set of equations. However, it's not as bad as it looks, because we've got a q dash dash over... yeah, sorry about that, I had an aeroplane going over. I thought I'd better stop recording. Where was I up to? Yes, q dash dash over q, and I'll figure out what that is there. So we've got this formula here, and what I'm going to do is I'm going to pass it through a differential. I'm going to differentiate it, and then I'll differentiate it again. So q of r equals that. So differentiate once, we get differential of sine is cos r over r0. Differential of r is just 1, of course. Differential of shine is cosh. So that comes out to be cosh r over r0. And then we'll differentiate it again to get differential of cos is minus sine, so it's minus sine r over r0. Sorry, it's minus 1 over r0. And the differential of cosh is plus sine, so I guess that goes to 0. And this is plus 1 over r0 shine r over r0. So what that tells me in either case, that q dash dash over q is equal to minus or plus 1 over r0 squared. Is that right? Have I got that right? Q dash dash over q. Yes, because we're dividing, we've got 2 powers. We've got a power of r0 here, and we've got 1 there. So it's minus or plus. I'm using this rather peculiar symbol. I'm used to writing that, but I'm writing it the other way around, because the first solution that we have, the eraser is not working. Oh yes, here we go. The first solution that we have, the sine, has got the negative sign, and the shine has got the positive solution. So q dash dash equals this nice little expression here, which of course, and I need that for this term here. So let me rewrite that, and what we've got here, eraser's not working again, OneNote is not performing as it should do, it's driving me nuts. There we go. So now we've got a double dot over a plus 2 a dot over a minus 2 over a squared, and it's q dash dash over q, which was 1 over r0 squared. So I can put the r0 squared there, and I guess I should take account of the sign, plus or minus. And of course, because it's a it's a minus sign, so the plus or minus turns into a minus or plus. And what does that equal? That equals cosmological constant minus 4 pi big G rho 0 plus p0. There we go, some beautiful equations here. So we can get rid of this one. Oh no, I meant to do this. Just a minute, I need to do that. Get rid of that one. What we've done by virtue of our simplifications, we've reduced it down to 2 equations now in an unknown. We've got a equals a of t, and it looks like it's overdetermined because we've got 1 unknown and 2 equations. However, what these equations include, but I've not made explicit, I've not made reference or use of the fact, is that rho 0, which is the density in the rest frame of a fluid, is a function of time as well, and the pressure is a function of the pressure, is a function of the time as well. So now we've gone from having 2 equations and 1 unknown, we've actually got 3 unknowns. We've got a, rho and p, and we need another piece of information to close this. Well, the other piece of information is actually embedded in the Einstein field equations, but it's easier to think about it from a physics perspective rather than a mathematics perspective. What we need to do is to link rho and t somehow. Rho and p somehow. We need an equation of state. Equation of state. Somehow. And you'll be used to these. From physics, we've got PV equals nRT. Pressure times volume equals number of moles times, I think that's the Rydberg gas constant times the temperature. I usually think of it in terms of P equals rho gamma minus 1 E. That's my equation of state, where that's the density, that's the adiabatic gas constant, and E here is the internal energy, and that's the pressure. I tend to use that one in my work. In any event, what we're doing is trying to link the pressure with the density, using the properties of the fluid. So what I'm going to do is, rather than try to take one or other of these equations of state, what I'm going to do is use the Einstein field equations directly, because they have got conservation of mass and conservation of mass energy built into them. Conservation of mass energy is a logical consequence of the Einstein field equations, and I'm going to show you how to use that in the next screencast. So I'm going to stop there, and the reason I'm doing that is that I want to be able to close this system of having 2 equations here, that equation and this equation here, and I've got 3 unknowns. I've got A, I've got rho, I've got P. I need an equation to close them. I could go back to the Einstein field equations, but you miss a little bit of physical insight, which I'll show you in the next screencast. So I'm going to stop there and do it in the next screencast. Stop.